next, I am excited to welcome Sina Kashuk, Senior Vice President at Help of Unfolded, and Isaac Brodsky, Principal Engineer at Foursquare. And they're going to be talking about how geospatial analysis can be challenging and time-consuming, and how new technologies help solve these problems. Get excited for behind-the-scenes look at how the latest innovations in geospatial data science will transform decisions like site selection, with a unique chance to see technology in action. So be sure also to stop by Foursquare's booth by navigating the homepage and top page of the sponsors tab. And looking forward to an exciting talk to reveal, and over to you, Sina and Isaac.
Hi, everyone. Thanks for joining this session. My name is Sina Kashuk. I'm head of Unfolded at Foursquare. Prior to Foursquare, I was co-founder at Unfolded. And before that, I was a data scientist at Uber and a couple of other organizations such as DataKind. I'm here today with my colleague, Isaac Brodsky.
Hi, I'm Isaac Brodsky. I'm a principal engineer for Unfolded at Foursquare. Prior to that, I was one of the co-founders of Unfolded, along with my colleagues Sina, Shan, and Ib. And before that, I was working on marketplace data systems at Uber. Throughout that time, I was also very involved with the H3 open source project since about when it started a few years ago at Uber.
Thanks, Isaac. And with that, we're excited to launch Hextile, the next generation of tiling system. So what is Hextile? Hextile is an analytical tile that is built on top of H3, open source project developed by Uber. H3 was designed for a special indexing purposes. And so the Hextile is actually well optimized for spatial analysis, and especially enrichment. If you think about it as it's a combination of many small little hexagons that are representative of that location. And that location itself can have, I don't know, billions of points associated with that specific hexagon. And what Hextile does is group buying at every level of a zoom, if you will. So if you are, let's say, in zoom level 10, it will get a hexagons level 10, and it would aggregate as many as data that is existing in that and represent it as a hexagon in a browser. Of course, with that, it will come a very high performance because the data was pre-processed. And also, these tiles are having this beautiful property of being tabular. And when they're tabular, as a data scientist, we all say data frame, right? So they can easily translate to data frame format, right? And if it's in data frame, it's much easier to manipulate it, play around with it, and even work with it. So with that, why we built Hextile? It's mainly built because of the pain point that we had ourselves. Either when I was working at Uber, even prior to that, one of the challenges that exists when I was doing a spatial data science was that the data was always coming in different shape and form. It's very hard to unify it. And even if you unify it, it was hard to store it. If we had a global data set, it's very hard to store the data and even process it and doing analysis with it. It's quite hard to deal with this just spatial data because the complexity of it itself. And even when you're done with the analysis, how you would even visualize that. And so putting all of those aside, now if you have temporal data, if you have a spatial temporal data set, then it's even harder to play with. It's harder to work with. So Hextile is here to solve this problem. I'm going to start with unification. Why is it important? Think about it. The real world is a very complex word, and if you want to represent that, you need to abstract it in one shape and form. So there are shapefiles for that. For example, you can abstract it as a point, line, and polygon. There are also grid systems that you can abstract that to. So you can have it in Mercator system. Even you can have it as S2 cells developed by Google, but also you can do it as H3. We believe H3 is the right way to go compared to any other system. Of course, it has its own trade-off, but it's the best for analytics, if you will. So I'm going to give you an example. So if you have elevation data, which is raster file, And if you want to transform that to H3, it's pretty straightforward to do. You can use the H3 library that exists. We also have a service for that we can do it for you guys. And let's say if you have a census data that is polygon data set, you can also translate polygon to H3. And then if you have noise data, and let's say this is a 311 noise complaint data set, you can also have that point data to be translated to H3 as well. And then you can overlay these three data sets together. You can join them, and you can create new metrics with that. You can do analytics with it, and anything that you can think of. So it's much easier now to deal with shapeless, quote unquote, data set. You don't need to be worried about the shape anymore. You don't need to be worry about the systems and coordinate systems and all of the complexity. Also, if you think about it, even if the data is in the same format, let's say they both are, let's say we're talking about zip code versus census tract, right, which is administrative boundary, right? Even combining those two data sets is quite a complex. And Isaac will talk a little bit more about that toward the end of this presentation. But the idea here is if you translate anything to H3, then you have one system to deal with, and then you can do all of your analysis in that system. So of course, if you tessellate the whole world with H3, the data can get quite big, right? Or even the data itself, as if you had even latitude and longitude data, if you have billions of data points, how you would be able to actually process that, how you would be able to bring it to the browser, is quite hard. And at Unfolded, we have also a studio, which is a front-end application. So for us, it was very important to build a system that can actually break down the data to small pieces of it and then bring it to the browser. And those pieces are the tiles. So hex tiles are enabling us to have a limitless data, literally limitless data in your browser with any resolution that you want. You can go from meter resolution to tens of kilometers, right? So, and that's a range of any analytics that you want to do. You usually don't want to go higher resolution than 5 meter, which is the resolution of a GPS, or even 1 meter. And again, being able to tile that data and compress that data in this tile system and just bring it to the browser is a key point for this system. So storage is much easier, right? And then you don't need to be worried about storing, because if you have this as a flat file, as a very simple file, then you would be able to actually store it easily, storing massive data easily. And also, because it's a tile base, now you can have it to be run in a parallel system, because you can think about each tiles are sitting in a partition, and then you can be able to actually run the full partition run the multiple partition in parallel, and being able to actually run your analysis in a quite of a fast way. So it's enabling for multi-processing. And with that, let's say your analysis is done, everything now, because it's again parallel, it's easy to visualize it, bring it to browser, as I mentioned, and be able to share it with others. At Unfolded the Studio, we are able to actually visualize your hex file, and then you can click a button and being able to share it with anyone you want. Either if you have an enterprise account, you will be able to securely share it internally, and if you want to even publish it, you would be able to publish it with password protected publishing system that we have. So it's exciting technology, and it works really well with the other stacks that we have at Unfolded system, or Unfolded platform, if you will. So we mentioned about all this powerful distributed system that we have, but beyond all of those, the real world is a dynamic world. It changes over time, right? And if you think about it, the weather and or the fire, wildfire, the one that you're seeing in the screen right now, is a wildfire that's happening in Africa over 1 year, over the year of 2021, of course, built by or partner Contour. And so the idea here is, like, as you can see in this map, the pattern of the fire is changing over time and space. So it's quite hard to compress and represent such data set. So hex files are able to actually do that quite nice, because they're analytical. You would be able to actually have animation on top of your data, and you would be able to have the temporal data associated with your data. And with that, you can solve a lot of interesting problems that we couldn't solve in the past easily. So example of it, if you're an insurance company, you're interested on exposure to the risk of your client, you would be able to actually path the movement of your client over space and also over time. In a daytime, nighttime, weekend versus weekday, you can calculate your exposure or risk exposure in different hexagon, and you would be able to enrich, or you would be able to join that data with each individual customer, right? So you would be able to have the master data. You would tile your data, and the master data, which is the exposure to or risk exposure, and then you will have your client data, and you would run both data together, and you would be able to do an easy join. So this kind of work was quite impossible, honestly, in a previous system, but in Hextile it's quite natural to it. You can easily do that. So how it works, I'm going to pass that to my colleague Isaac to go through a couple of examples and deep dive on them.
Thanks, Sina. Yeah, so the first part that I want to make about how this works, next slide, please, is about this unified analytics that Sina touched on a little earlier. So unified analytics is really important to why I think that Hextiles are a tremendous advancement in delivering spatial data. As Sina mentioned, there's a lot of different sources of data that we want to do analytics based on, whether they're from rasters, such as from remote sensing satellites or airplanes, from points that could be from GPS traces, such as in Sina's example about a truck moving across the country, or in polygons, which could be administrative boundaries, census block groups, zip codes, things like this. These all come in different geometries, and our solution for working with these in analytics is to project them into the same H3 grid. Having this data in the same H3 grid in the Hextile system means that when we want to bring different data sets together, it's a very straightforward matter to join these data sets. And this is a really key feature of the Hextile system. Next slide, please. In addition to having the structure that makes it very useful for spatial analytics, we also felt it was really important for Hextiles to be both performant and flexible. And what I mean by performant is we want to be able to look at these very large data sets, bring them to a browser, bring them to the front end so that we can actually view them and explore them in a very quick manner. So not waiting a long time for updates, waiting a long time for data to come back. We want that to be a very fast and efficient experience. And we also want to preserve flexibility, which is why we chose to use some very modern, very recent data transport formats like Apache Arrow. This allows us to not only bring this data very quickly, but also to preserve a lot of the analytical capacity of this data, because we can bring this as analytical tabular data to the front end. So we're not just bringing a visualization of the data, but actually this analytic data itself, which we're going to be demoing in a few moments as part of our presentation. Next slide, please. So taking a step back of what a tiling system is, we mentioned that this is really useful for working with very, very large data sets. And what tiling does is it takes our knowledge of some really key points about these geospatial data sets and applies it to the organization of those data sets. So we know that data sets that are geospatial can have data distributed over a wide area, and we want to look at them at different resolutions. We want to look at them both at maybe a global or very coarse resolution, but we also want to look at them at very fine resolutions. And when we do that, we want to zoom in and look at more and more data, look at more and more precise data. Next slide, please. And the Hextile system is very well suited for this. We used our knowledge of how the hierarchical H3 grid system works and how we can most efficiently use that in order to bring in just the data that's needed, as well as the precision of data that's needed for our analytics. Next slide, please. So we've kind of touched on that there's some other geospatial data formats out there like raster tiles and vector tiles, and I felt it was important to kind of point out how does Hextile compare to these. Raster tiles is a tiling system which is seeing pretty widespread use, especially for remote sensing data. So this is data that's from satellite rasters or from airplanes, things like this. And it can be used a lot for meteorological use, for environmental use, things like this. Some of the difficulties with raster tiles are that some of the joins and display of the data can be a little challenging because these rasters come in a really wide variety of shapes and projections and pixel definitions and things like this. It can be difficult to mosaic these data sets together so that you can view a single composite image, and it can be difficult to join these data sets together. This is kind of its whole area of expertise in terms of how to work with these tile sets, and so that makes there be kind of a level of introduction that's needed to really get working with raster tiles effectively. Vector tiles allow us to bring really precise geometry because they're defining individual points and lines as opposed to raster tiles that are pixels. And this makes them really well suited for navigational uses and for administrative uses. But if anything, the join situation with vector tiles, I think, is even more challenging. Vector tiles require both an algorithmic approach to joining it, of understanding how different points and geometries intersect and interact with each other, and also it can be very computationally expensive to do these types of joins and do these types of geospatial operations. Hex tiles, by comparison, is really focused on this analytical use case, and so it uses a standardized geometry using the H3 grid that makes it very, very easy to do joins of data. It also has this focus on bringing tabular analytical data to the front end. So it's really focused on how to efficiently encode that data and also have flexibility for for what types of data that we want to be bringing to the front end that these other tile systems have to varying levels, but I think is best demonstrated in hex tiles. Next slide. Another point that I want to touch on is the spatial temporal aspect of hex tiles. So for our hex tiles, as Sina mentioned, we saw that these data sets that have a temporal dimension, that have a time dimension, were some of the most challenging data sets to work with. And so we wanted to address that in hex tiles. We did this in a couple of ways. One is by making sure that the tile format, the tile structure, I should say, supports temporal queries and for looking at different ranges of time, so that we're able to bring the same partitioning and tiling approach to time that we bring to the spatial dimension. And this allows us to work with very large time ranges, and also to bring temporal data to the browser and to the SDK when we're working with these geotemporal tiles. And that allows us to do analytics and animation on top of these very large and very challenging data sets. Next slide, please. As I just alluded to, hex tiles is something that you can use both in browser, so the Unfolded Studio platform, just very smoothly moving around these tile sets, as well as in SDK format. And we're going to be giving you some demos of these in just a moment here. And of course, the SDK form means that kind of any programmatic access that you can think of on top of this way of delivering geotemporal data is available to you. So whatever type of machine learning or analytics you'd like to do on top of it is possible. Next slide, please. So I think after this, we're going to cut over to doing a few demos. I'm going to start off with this weather data set. So this is looking at precipitation across the United States over the month of September of last year. I'm not sure how well this will come across in screen share because that's always a little dicey, but you can see this animating across the United States, and I can watch these storm systems move through. And as I mentioned, this is a tiling system, so I'm able to actually zoom in here and get additional information about additional spatial resolution, I should say, of this storm system, for example, here moving through Arizona. I can also switch off of the storm data and look at another data set. I'm going to look at elevation here. This one has a much wider geographic extent, not quite worldwide because of the source data that we used, but obviously much broader. You can see here that I can just very quickly move around the world looking at this very, very large data set. And we're not just bringing a visualization of this data set to the browser, but we're actually bringing this analytic data straight to the browser. So I'm actually able to do all the things that I would do in Unfolded Studio with this data set, such as do filtering and actually get real-time feedback from the application about which areas, for example, have a higher elevation. So I can use that to identify some mountain ranges, for example, zoom in on them, get more detail on what these mountain ranges look like. And of course, I can also remove my filter again to get access to this higher resolution elevation data, in this case, looking at kind of northern Italy and Switzerland area. I'm going to switch over to showing something slightly different in Unfolded Studio here. This is a map where I've brought in some data from the Census 2020 redistricting file. So I have here the Census 2020 population as well as some race demographic information. I also have some information on group housing and housing units from the Census redistricting file. And I also have a data set from Foursquare showing visits to various points of interest and businesses around the New York area. So I'm going to come back to this population and demographics hex tile data set. And I'm actually going to choose to extract this data set to my browser. So I'm going to select this, and I'm going to say that I want to work with this area of the data set. And I'm able to very, very quickly bring this entire table of data back to my browser and work with it as a fully tabular data set. So I can, of course, get all of my column statistics and page through my data set here. This is just the demographics data, though, and I want to work with some of these other data sets as well. So I am going to give a little bit of a disclaimer that I'm not really a data scientist by trade. I really focus more on the engineering side, so you'll have to humor me in my attempts at data science. But I'm going to join this demographic data with the housing data and see if I can learn something from that. So I select to join these two data sets together, and after just a second, again, my data table is enriched with this additional information about housing and group housing characteristics. Now that I have this data set joined, this data is available in the same table, and so I can actually define metrics that relate these two data sets. So I'm going to look at population related to the number of occupied housing units. And my theory with this is that this will show me areas where there are more or less dense housing units. So I've divided the population by the number of housing units for each cell. So I'm going to add this to my map. And again, this is dividing across between fields on two different data sets, on the demographic data set and on the the housing data set. So when I do this, I can see a few areas kind of popping out to me on the map. One is Manhattan, and the other is Brooklyn, showing up as having very low values. And my hypothesis for that is that these areas tend to have more smaller apartments, and so this tends to have fewer people per housing unit on average. I also have this visits data that I mentioned as well, and so I'd also like to do a little analysis using that. So again, I'm going to join my demographic data with my visits data, and I'm going to select a join on this H3 column. And I'm going to get a new table back of my demographic data enriched with my visit data, which again are coming from very different sources, one from Census and one from Foursquare's visits data set. When I do this, I can define another column here, which is I'm going to look at the relationship between the number of visits and the population. So I'm going to look for areas that have, for example, very high number of visits, but very low number of population would be brought out by this. So I add this to my my map, and again, I'm going to visualize that metric that I just created. And I can continue, exploring this data in Unfolded Studio. So I can look at, for example, this metric, and I can see that there's this very long tail here, some areas that have very high outliers of number of visits relative to the population. And if I filter for that, I can very quickly pull out airports, for example, in New Jersey and New York, which makes a lot of sense because these are areas that there's a lot of people moving through. There's a lot of people coming to those points of interest, but at the same time, people tend not to live near airports because of noise and other reasons. One more thing I wanted to show here is this global fire map made by our partner at Contour. So this map is showing global wildfires across the world, and I can actually play through this map here in my browser, and I can actually see how these fires are evolving over time. And not only do I have this data available for animation, but I can also zoom in here, for example, zooming in on the continent of Africa to get more spatial precision and more spatial, finer spatial precision of how these fires are evolving over time. So with that, I'm going to hand it back to Sina to demo hex tiles in notebooks and with the Unfolded SDK.
Okay, thank you so much, Isaac. And now let's have an example in Jupyter Notebook. So what is the problem here that we're trying to solve? We're trying to find out places that are lookalike universities. And how we're going to do that is by building a classifier to predict probability of being university based on features like age and vicinity to public transportation. Is a quite of a simple, kind of scope. So what I'm going to do is I'm going to pull my map on the right side, and of course you need to authenticate to the map. So we'll do that. And what I have here is a simple classifier that I have. Basically, it's a random forest classifier. And what I'm going to do is I'm going to try to predict university proximity, and then with that I'm going to run the model I'm going to start in New York City, and then I'm going to run the model in San Francisco to see how's the performance. So what we're going to do here is we're going to use age, transit, and education as the three data set, and as part of the education we have university proximity. I'm going to have a threshold for to say, let's say if the proximity is more than 95%, then that is university. And we're going to run this model. As you can see, we have about 1,000 cells, 4,000 was fetched, and you see how quickly it enriched the data with age, transit, and education, and run a model. And as you can see, the result is quite interesting. You can see here's Columbia University, and this is NJIT, and a couple of other universities here. And then what I can do, I can then run this model in San Francisco. I have a bounding box here that I'm going to go to, enrich it, and look at without again knowing anything about this location rather than age and vicinity to public transportation. You can see it easily captures. Let me just turn off this layer. To make it a little bit more visible, I'm going to reduce the opacity so you can see clearly what is happening here. So you can see this is UC Berkeley. This is Stanford. If I zoom in, and a couple of other universities like San Jose State University, and I think this might be Santa Clara. So again, I did not. Yes, it's a Santa Clara University. I did not necessarily give any information about the university, rather than saying in New York City, the predictors for university is probably airport proximity, bus proximity, and metro proximity, as well as age of 18 to 29. and percentage age of 5 to 17. So it's interesting because yeah, you can think about age of 18 to 29 to be age of the college, but why 5 to 17 was selected? Is it a positive effect or negative? You can actually quickly look at the features that I was running here, and to see, for example, let's look at the age of percentage age of 18 to 29. You can see, yes, there are quite a representative of those population, but there are other areas that are in that age but are not selected, and that is because the random forest is able to actually predict that the age also should not be in a range of 5 to 17. So if I look at the percentage age of 5 to 17 for places that are universities, you see less of that age distribution. So it's a very simple, again, example of how you can use the studio and Hexal to be able to predict against certain probabilities, or I would say in this case is more of a lookalike analysis. You can do the same analysis for let's say Starbucks. If you're interested to know what are the places that they have a Starbucks, where are the places that are lookalike a Starbucks location, you might be able to build a model and figure out places that are considered as high probability of in a Starbucks but not actually having a Starbucks. In that case, then those are considered as opportunity areas. So you can see how I'm using kind of machine learning to build this to some extent unsupervised, because I'm not sure about where I'm going. I'm doing some sort of clustering using the random forest. And it's a very good example of how you could actually use again certain features to predict what different metrics that you're interested in would be, right? So yeah, with that, we'll pause here, and if I go back to presentation, I think we have one slide at the end, and that is a thank you. Thank you so much for attending this session. We really appreciate your time, and we are very excited to see what you guys can build with this technology. Of course, this is the very first version of Hexal. We're having many plans to come, like having more machine learning capacity and so on and so forth. So, but we're excited to see how this technology can help the world and help your work to be faster, easier, and more joyful. Thank you so much.
Thank you so much.